All right, so our goal is to analyze an LC circuit using Lagrangians, and the foremost step in that is finding the Lagrangian of the LC circuit. So we need a kinetic energy term and a potential energy term. For kinetic energy, we're going to use the fact that we know the voltage drop across an inductor is L di/dt. We're going to multiply that by some small dq, because we're looking at what work does it take to move a charge through that inductor. That work will then be imparted as energy on the particle, and the particle is moving, so it will be a kinetic energy. So dq times E, we're going to multiply that dq over here as well. This should be a small de, right? It's not full E, small de. I divided both sides by dt, so we get one extra dt term here. dq over dt is I, so we're going to have a L integral of I, and then these two dt's cancel, so di. Integrating this, we're going to get E equals 1/2 Li squared. I is q dot, so we're going to have 1/2 L q dot squared as a kinetic energy term. The potential energy of charges stored in capacitor is q squared over 2c. I'm just going to give that as a given value. I do not want to derive it. Very basic physics too. If we're solving the Lagrangian, it's going to be ke minus u equals 1/2 q squared minus q squared on 2c. And that is the Lagrangian that we were looking for. So in part B, we are actually solving the Lagrange equation that we just found right here, boxed in. The partial of the Lagrangian with respect to q is going to be, this term goes away, so the 2 is going to come down. We get 2q on 2c, the negative here is still carried over. 2's are going to cancel, you get negative q on c. I'm going to write this as negative 1 over c q. It'll be more familiar for diffie q in a moment. And here we have the time derivative of the Lagrange with respect to dq. Dot is the time derivative of L q dot, since the 2 comes down and L q dot stay. And then we just bump up the order of q one time when we take its derivative. So writing the differential equation that we have here in terms of the actual Euler-Lagrange equation, it's going to be negative 1 on c q minus L q double dot equals 0. If we move that over to the other side, we get L q double dot plus 1 over c q equal 0. When solving differential equations, we'd like to have the leading coefficient be 1. So I'm going to divide the whole thing by L to get q plus 1 over LC, q double dot plus 1 over LCQ equals 0. This is a easy diffie q to solve with undetermined coefficients. It has a general solution of q of t is equal to q naught, a constant determined by the initial conditions, cosine of omega naught t plus some phi. We don't really care about phi, that's a shift angle, we care about omega naught. Omega naught comes from rewriting this as 1 over omega naught squared q equals 0. So if omega naught squared equals 1 over LC, then omega naught equals 1 over the square root of LC, which gives us a resonance frequency, which is the angular frequency, which matches circuit analysis theory of the resonance of an LC circuit. All right, and the final part that we examine is for the case of an RLC circuit where we have added a resistor. In this case, we must modify the Euler-Lagrange equation to deal with a dissipation force added here. It is the dissipation of power through the resistor as it loses energy. Ri squared is correct, but we tend to represent it in terms of the Rayleigh dissipation function because we like the 1/2, it makes things easier. These clean each other up after the differentiation. So we get a new differential equation, L q dot squared plus R q dot plus 1 over c q equals 0. This is still undetermined coefficients, it's just a lot more work, and it has a general solution of qt equals e to the negative alpha t times a cosine omega dt plus b sine omega dt, where omega d is the damping oscillation frequency, and alpha is the damping coefficient, the damping oscillation damping coefficient. R over 2L comes from the quadratic formula. Omega d comes from the square root of omega naught squared minus alpha squared. So omega d is equal to the square root of 1 over LC, square that, and we square this, minus R over 2L squared. And this, combined with this, plugged in everywhere that they appear in this, does match the harmonic oscillation of a spring system.